Welcome friends to my YouTube channel. Now on my last lecture I have discussed about adiabatic demagnetization process and there I told the principle of demagnetization process and also find out the amount of cooling produced. Okay. Now in today's lecture I shall going to discuss few important problems related to JT effect. Okay. So let's proceed. Our first problem is that we have to find out that for small change in pressure delta P, the corresponding change in temperature can be written in this way. V by Cp alpha T minus 1 into del P. This we have to prove that for a small pressure change delta P, the corresponding temperature difference can be written in this way. Okay. So we can easily write the Joule-Thomson coefficient expression where we can write it dt this equals to 1 upon Cp T del V del T pressure constant minus V into dV. Now when the pressure and temperature differences are very small, this can be replaced by triangle delta, the triangle shape, that is del T del P, this. So we can write it del T this equals to 1 upon Cp T del V del T pressure constant minus V into del P. Fine. Now we all know this, that alpha, this is volume expansivity, can be written in this way: increase in volume per unit rise in temperature keeping pressure constant. This is the volume expansion coefficient, or you can say volume expansivity, that is increase in volume per unit rise in temperature keeping P constant. So from which we can easily write del V del T pressure constant, this equals to V alpha. So if we substitute this value in this equation, so what we get? Del T is equals to, kindly ignore the noise which is coming from outside. So 1 by Cp T V alpha minus V into del P. So if we take V common, so this will be V by Cp alpha T minus 1 into del P. So this is the required relation. So this is a simple interesting problem. So we have to replace this term by alpha. This is what we do here. Okay. So this is our first numerical. It's simple and interesting. Okay. Now let us move to the second numerical. That is, we have to show that for an ideal gas, delta T will be 0. I think I have told it previously, so I can also do now. Now we know that previously we derived this relation del T V by Cp alpha T minus 1 del P. Fine. Now write down the ideal gas equation for n mole gas, PV equal to nRT. So differentiate this with respect to T keeping P constant. This is simply nR. P del V del T pressure constant, this is equal to nR. Or you can write this alpha into V. This is simply nR. Again you substitute nRT instead of PV. So what we get? Alpha nRT, this equals to nR. So what you get? Alpha T equal to 1. So substitute this value in this equation. What we get? V by Cp alpha T is 1. So 1 minus 1 del P. So this is simply 0. Okay. So simple. So write down the ideal gas equation, then differentiate this expression with respect to T keeping pressure constant. You write this. Now substitute nRT instead of PV, you will get this. So by putting this value of alpha t in this equation, the result will be obtained. So we obtain the result. So this is also an interesting numerical. So 1 and 2 are related to same problem. Okay. Now let us move to the third numerical, that we have to show that mu s this equals to mu plus v by Cp. What is mu s? Mu s represents the increase in temperature per unit pressure keeping entropy constant. Since there is s, we have to put s here. So we can use the JT coefficient expression mu, this equals to 1 by Cp T del V del T pressure constant minus V. Now what we can write? We can write mu Cp this equals to T del V del T pressure constant minus V. So from which we can write mu Cp plus V this equals to T del V del T pressure constant. So give it a name, say 1. Okay. So I can write it here, mu Cp plus V this equals to T del V del T pressure constant. Okay. Now starting from the second TDS equation, T into ds this equals to Cp dt minus T del V del T pressure constant dt. Now if we divide this expression by dP, then what we get? Cp dt dP minus T del V del T pressure constant. Now what happens at constant entropy? When S is constant, what happens? This term will be 0 and this we can write as del T del P S minus T del V del T P. So from which we can easily write T del V del T pressure constant is equals to Cp del T del P S, and this is nothing but mu s. So we have find that this term is equal to Cp mu s. Now substitute this in this expression, what we get? Cp mu s. Now just do one more step, then the result will be obtained. Okay. So we get this mu Cp plus V this equals to Cp mu s. Now what will be my mu s? Just divide both sides by Cp. So we obtain the result. Okay. Mu s this is equals to mu plus V by Cp. Okay. Now just another problem, that given that P this is a function of this, we have to show that S increases with volume. S increases with volume. Now one thing I must say, that there are few numericals that are both common in this chapter, and also you can do these numericals in Maxwell's relation chapter, no matter. There are few common problems. Now from which we can write del P del T volume constant this equals to f of V, and again f of V means P by T. Now from Maxwell's equation, what can write? Del P del T volume constant means del S del V temperature constant, this equals to P upon T, and this is positive. P by T is positive because by keeping volume constant, if you increase pressure, then temperature increases according to law of pressure law. So this is p by t positive. So clearly what we see, if the right hand side is positive, then S increases with volume. Okay. So this is our numerical, fourth numerical. Now the next thing I am going to discuss is the very shortly I will discuss it. One thing, liquid helium. What are the basic, at first we will discuss the basic properties and uses, then we will discuss the applications. Okay. So if you go into the basic properties of liquid helium, so what are the basic properties? You all know, higher secondary students also know it, that liquid helium shows maximum density. Liquid helium shows maximum density of liquid helium is this, gram per cc. This is exhibited at a temperature, this. Okay, you all know it, higher secondary students also know it, that at 2.2 Kelvin temperature, liquid helium shows its maximum density. Okay, and thereafter with decrease in temperature, the density decreases. Okay, so with decrease in T, its density decreases. So this is the first basic property, that maximum density of liquid helium is this at 2.2 Kelvin. Okay. Second property, that also you know, that it shows a transition at temperature 2.18 Kelvin. It shows a transition at this temperature. This temperature is called lambda point. Okay. Above lambda point, it is known as helium 1, and below lambda point, it is known as helium 2. You also know it, that at this temperature 2.18 Kelvin, it shows a transition. Okay, and this temperature is called lambda point of liquid helium, which is a second order phase transition. And above lambda point, helium is known as helium 1, and liquid helium is known as helium 2. Okay, so maximum density is this at the temperature 2.2 Kelvin, and with decrease in density, or temperature decreases, or with decrease in temperature, density decreases. And at this temperature 2.18 Kelvin, helium shows a transition. So above the lambda point, that is this temperature, it is called helium 1, and below it, it is called helium 2. So these are the few basic properties, few basic physical properties of liquid helium. You must remember these two. Okay. Now what are the basic uses of liquid helium? The first basic use is that the common use of liquid helium is to test the purity of various metals. Testing the purity of various metals. That is, if the metal is pure or impure, you can judge it by using liquid helium. Liquid helium is used to test the purity of metals. This is the first use. The second use is that superconducting computers are made up of liquid helium. Okay. In superconducting computer, which are more faster, which superconducting computers are made up of liquid helium. Made up of means, that means it contains liquid helium. So liquid helium is used in constructing superconducting computers, which are very faster, that we all know, which are very faster. Okay, so one can test the a metal whether it is pure or impure by liquid helium. Also, they are used in superconducting faster computers. And another important use that it is used to cool the electromagnets. Okay, so that no so that there is no flow of huge current through this. Okay, if we cool the electromagnets, then we can prevent the huge flow of current through the coils of the electromagnets. Okay, because what happens when huge current passes through the coils of electromagnets, we know that irreversible joule heat loss occurs. So great amount of heat is produced that can damage the electromagnets. Okay, so in order to prevent the irreversible joule heat loss, we must cool the electromagnets by using liquid helium. So these are the basic uses. Okay, testing the purity of metals, or you can say cooling of electromagnets so that no huge current flows through these coils. And superconducting computers are made up of also liquid helium. Okay, so these are the few basic properties of liquid helium and its uses. Okay, now in our next class I shall going to discuss few other issues, and that will be the last lecture of low temperature physics, and with this lecture I shall finish the thermodynamics course of BSc. Okay, now in our next class this will be done. So if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, thank you.